the sediment to be generated. And that sediment generation based on the weathering processes and the liberation of different kinds of cations and anions in the system, which basically from the land to sea, how the balance of this ionic system as well as the sediment that we basically discussed in the last class. Now today we start our class just from the because the sediment, once the sediment is generated, then when as a sedimentary geologist you go to field or you are given a sedimentary rock, the first thing, particularly I am talking about the plastic sedimentary rock, first thing you have to identify what is the rock. Now that rock identification depends in sedimentary cases that fully depend on the size of the grain of the rock. Now see the difference. When you basically name a igneous rock or a metamorphic rock, now what you basically do, yes, I do agree that in a metamorphic rock you say it is a gneiss, it is a schist, but even then when you talk that it is a schist or a gneiss, even then you say it is a chloride biotite schist, it is a quartz mica schist. So the name of the minerals, they are always associated in the rock. That is quartz mica schist, chloride biotite schist, like that, hornblende gneiss. So like that, the mineralogy is always associated with the naming of the rock. Same is the igneous rock, that unless you identify the minerals present in the rock under thin section, then you cannot say, oh, it is a granite, it is a basalt, it is a diorite, it is a anorthosite. It all depends upon that you identify the mineral. Yes, mineral identification absolutely has a role in the sedimentary rock as well, but for the primary naming of the rock, really mineralogy take a back seat. You always name it is a sandstone, it is a siltstone, it is a shale, it is a conglomerate. Do you name the mineral? You really do not name the mineral. So essentially, the naming of a sedimentary rock in a large scale depend upon the size of the grains present in the rock. And that's why the size determination of the grain becomes a huge important factor in a sedimentology, that how really I get to know that this is a sandstone, because in the nature you have all the different kinds of sizes. You think of a large boulder, which if you go to the Himalayan rivers or those sides, then you get the huge river boulders, and you get the mud and the silt, and there's a huge panorama of the sizes that you get in a sedimentary realm, right from the huge boulder to the finest of the grain size, that is the mud size. So then in the early days, because the grain size is a very important factor in a sedimentary rock, then the question came to the mind of the people that how to designate the different sizes. And problem was that the size range was so huge. So to determine that what are the size limits, that became a very difficult task. You cannot understand it right now, but the people who actually did that in the initial time, they faced a huge problem. The problem is that how to define a scale for the size of the sediment, because the size range is huge. It is several centimeter, even to a meter scale, a grain, a boulder, several meters diameter boulder, to a millimeter scale, that is you get the mud or the silt or the mud. So then the people who first started it, that is Uden and Wentworth, they first attempted, it's a huge credit to them, that to identify that what will be the scale and how the different sizes of the grains, they will be named by different terms. So it is a huge credit to them. They first start that this will be the, and what they did, that they identified that boulder, cobble, pebble, granule, sand, silt, clay, or sorry, mud. So what they said, 256, 64, 4, 2, 1 by 60, 1 by 2. all this is in millimeter. They basically, is it visible? Whatever I am writing, is it visible?
Yes, sir.
Okay. So what they say, they basically define that there is a geometric scale. It is not a arithmetic scale, that it is a geometric scale, and this geometric scale that is actually the device in the millimeter scale. In the millimeter scale, they devise for the grain size from the boulder to cobble, pebble, granule, sand, silt. Now the thing is that now the question is that it was very well designed and people must have been very happy, but people were not very happy. People were not very happy. Why they were not very happy? And you all know there is another scale, but it's called the Crumben phi scale. Crumben, what we call the phi scale. Now, when there was one scale, what was the necessity of the other scale? And why there was a necessity of other scale? Can anyone tell me? You all know now there are two scales. One is a phi scale, another is a wooden Wentworth scale. Is it known to all of you?
Yes, sir.
Yeah, but
yes, sir. Yes, sir.
When there is one scale, another scale necessity was why? There was a necessity of another scale. Okay.
Because in the Wentworth scale, for the finer particles, it was difficult. And in the Crumben scale, it made it easier to compute for the finer scale particles.
Yeah, you are nearly right. Yes, what she is saying is that the most abundant grain size in nature, that is basically sand size. This is all of our experience, that most abundant grain size is sand size. And what is happening, the sand size is 2 to 1 by 16 mm. And that most of the sizes it comes in the fraction. And that in that time, in absence of computer or calculator, the calculation used to become very cumbersome because you have to calculate all things with the fraction. So that became a problem. So what they tried, that why not to make it the class intervals, that the boundaries of the classes, why not to we make it such that it becomes a positive integer? It becomes a positive integer. So this thinking process, that to make easy the calculation process, to avoid the fraction, that is why the Crumben scale that came into being. And what they say, that all these fractions, they are basically power of 2. They are basically power of 2. They are all power of 2. So the phi scale, that is said minus log e to the base 2. Now why suddenly in phi definition this minus sign is given? Why this minus sign is given? Because when you make it this minus, when you transfer all these different values which are the power of 2, this becomes minus 8, minus 6, minus 2, minus 1, plus 4, plus 8. Plus 4, plus 8. So what you are getting, that the maximum grain sizes, what you are getting, they will be becoming the positive integer. Positive. Just to make them positive, you basically make a negative sign at the beginning of it, so that you get the values as positive integer. And that's why that the scale is given phi is equal to minus log e to the base 2. And that's why the sand size. Then what is the sand size? Sand size is from minus 1 to plus 4 pi. Sand size is minus 1 to plus 4 pi. So very close, coarse, medium, fine, very fine. So -1, 0, 1, 2, 3, 4. So this is the entire sand grade. This is the entire sand grade -1 to +4. And within that -1 to 0, 0 to 1, 1 to 2, 2 to 3, and 3 to 4, then you call that the sand size, even within that you have very coarse sand, medium sand, fine sand, very fine sand. So that is further subdivided within the sand size between 1 to 4. Okay? Any question here? Or then I will proceed further. Okay. Now, when we have a size, then the question comes how to measure the size of a grain. How to measure the size of a grain. So the measurement of the size of a grain, that becomes very, very important. And as you know, there are different grains of different sizes, and that's why the size of the grain and how it will be measured, that becomes very, very important. Now, when you have a large size grain, that means you can measure it by means of the scale and vernier. For large, for a pebble, for a cobble, for even for a granule, I can easily make it pebble, cobble, granule. I can easily make it by means of a scale and vernier, considering it as a triaxial ellipsoid. Triaxial ellipsoid. So, if you have, this is a pebble, so you can have these, you can have these, and then you can have this. So you can directly measure that 3 different axes. That if this is a pebble and I cut it, I just cut it, and then I can measure the 3 different axes. I can measure it very easily. Now the problem starts when you come to the sand. When you come to the sand, then the question is how to measure the size of sand. It is very difficult to measure the size of sand either by a vernier or by a scale. So there are 2-3 things that we first define for it. The first thing what we define, that number 1, what is nominal diameter of a grain? What is nominal diameter of a grain? What is nominal diameter? Because when we say that we measure to know the size of a grain, we actually mean the diameter of the grain. By when we basically say that we try to measure the size of a grain, we actually mean the diameter of the grain. Now, what will be the diameter of a grain which is a mica grain, which is a platy grain, or a quartz grain which is near spherical in size, or a pyroxene or a hornblende grain which is more prismatic and elongated in shape? So how to determine the diameter of these different shapes of the grain? A mica grain, a quartz grain, a pyroxene grain, anything, it can be a grain, because sand is a size, does not depend on any composition. Sand is a size, does not depend on anything of sand or of that size, I will call it sand. Anything of that size, I will call it sand. Now I will ask you one question. Suppose I take a boulder and I start hammering on that boulder. So the boulder will get broken, and the boulder will get broken in different sizes. I go on hammering to that, and I go on hammering to that till the size of the sand is reached or size of the mud is reached. Should I call that as a mud? Should I call it as a sand? If I start hammering a boulder, sand is a size, mud is a size. So it is clear, boulder is a size, cobble is a size. So if I take a boulder and start hammering it, and so much.
Yes, we can say that, sir.
But we can say?
Yes, sand size.
I can say it is mud.
Yes, sir.
If I so mud is a size, and I can, if I hammer it with a boulder and take it to mud size, so mud is produced. You want to say that? You are sure about it?
Yes, sir. You can.
I will give my answer in 2 words. Number 1, mud is a size, but there is another connotation when we talk about mud. What connotation? The mud is normally formed of clay mineral, isn't it? Mud is normally made up of clay mineral. Can I produce a clay mineral by hammering?
No, sir.
Can I produce clay mineral by hammering?
No, sir.
No, sir.
No. What I can do, I can only change the size, but I cannot generate the clay mineral. So if mud connotatively is made up of clay mineral, then certainly I cannot make mud by hammering. But if mud is only considered in a mechanical way as size, then certainly I can make mud by hammering. So
but we can consider. Sir, but we can consider it sand, na?
Which one?
So the boulder
Yeah. For sand there is no issue. For sand there is no issue. In fact, though geologists will not agree with you, but engineers will agree with you. Engineers, they when they break, they keep boulder, they break it, and they break it in the form of the chips and then the sand grade. They say it is a sand grade material. But the sand in a geology, we basically see that when the sand it is produced by naturally from the source or during the transport process by hydrodynamic way. So that we call that it is the product of sand. Definitely, if I hammer it and produce that size, yes, in a stricter sense, if you say it fall in the sand grade, but because it is not naturally formed, I will not say that it is actually a sand. But I do fully agree that you can create a sand size grain by hammering a boulder. Okay? Now, since we, by means of size, we call that the diameter of a grain. By means of size, we mean the diameter of a grain. And as I said, the diameter of a spherical grain, diameter of a platy grain, diameter of elongated grain. How can I know what is the diameter of a grain? So the concept of nominal diameter that came into place. What is nominal diameter? Nominal diameter is the diameter of a sphere that has the equal volume with that of the grain. Nominal diameter is the diameter of a sphere having same volume as the grain. Same volume as the grain. This is what we call the nominal diameter. Now, suppose a mica grain that is settling. Mica grain is settling. So, the settling velocity of a mica grain will not be similar to the quartz grain. It will be equivalent to the much smaller size quartz grain. Suppose a quartz grain which is spherical, it will be settled very quickly than a mica grain which will be floating, and it will be taking more time than a quartz grain. So this factor, that how the diameter of a grain it is basically affecting its transport or settlement, that is a separate factor, what we also refer to as the effective diameter. One is the nominal diameter, another is effective diameter. Effective diameter. Now, what is effective diameter? The diameter which actually comes to play a role during the settlement of a grain. And this effective diameter will vary between a quartz and a mica grain. And the nominal diameter is the diameter of a sphere which has equal volume to that grain. And that nominal diameter concept is very well used both in the sieving as well as the settling, that I will be talking now. Now the sand size, how we measure the sand size? The best way we measure the sand size is by sieving. Sieving.
Sir,
Yes.
will you please repeat the definition of nominal and effective diameter?
What? Oh, please repeat.
Sir, will you please repeat the definition of nominal and effective diameters?
Repeat. Okay. Nominal diameter is the diameter of a sphere. You can write diameter of a sphere which has equal volume to that of a grain. I will further explain it. An effective diameter is the diameter which comes to play a role in course of settlement of a grain, settlement of different shapes of a grain. Now, let us see that we create a bank of seeds that is basically kept, and we basically keep the sample with a particular weight, samples of a particular weight that is kept on the topmost seed, and the opening of each seed that is actually known. Opening size of each seed, they are ASTM, American Standard. Opening size is known. That means any grain which is smaller than this size, it will pass through it and go to the lower seed, and any grain which is larger than the size of the opening, that will remain in the overlying seed. So when you put a sample and start shaking the entire bank of seed, mechanically or electrically, you will see that the grains, they will be divided between different fractions depending upon the size of opening of the seeds. Here, so it will be divided into W1, W2, W3, W4. So your W is now equal to W1 plus W2 plus W3 plus W4. So it has been now divided into 4 different fractions depending upon the size of opening of the seeds. Now I have done this. One of you are also doing the seed. Instead of 4, you have put 6 different sizes. So then the same sample will be divided into 6 fractions. W2, W3, W4, W5, W6, 6 fraction. So more the sizes you are inserting into it, you are dividing into your sample into more fractions. You got my point? That how much fraction you will be making your sample, that fully depend upon that how many sieves you are using in the bank and what opening you are keeping in the sieve. But can it go to the infinitely small size? No. It can go up to the size of 0.03 to 0.04 mm. 0.04 mm. Below this size, you really cannot separate the individual grain because there is a huge cohesive action and the grains, they get coagulated and the individual grain separation is not possible. So I can go separating the different fractions, but the lower limit of this sieve separation is 0.03 to 0.04 mm, below which the individual grain separation by sieving, mechanical sieving is not possible because of the extreme cohesive action and the separation of individual grain is not possible. So what do we do for grains which are smaller than this size? What do we do for grains which are smaller than this size? So first I talked about the boulder bevel bubble which you can directly measure. Then I talked about the same size which we measure by means of sieving. And the sieve help us in identifying the different fraction of the grains. We will do the practical exam. Sieving the possible, but sieving data say we will be doing the practical exam. A practical class, how we interpret the sieving data. Now, what will happen for grains which are smaller than that? For the grains which are smaller than that, we actually take the help of the process called settlement. 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 What we do? In a jar, we make a uniform solution of my sample. Uniform solution of my sample. I do the uniform solution. What is uniform solution? That if I take the density at different levels, then all the densities they are same. That is how we get we create a uniform solution of a particular sample. There is no variation in density through the entire solution. And then, if there is a grain and the grain is settling in a uniform solution, then what will happen? That the gravitational force on the grain, it will be equal to the resistive force against fluid. Resistive force against fluid. So these two will be, and that is what is Stokes law. Stokes law. The Stokes law says that if a grain, it is settling through it and it is not accelerating, it is a non-accelerating. It is not accelerating. If a grain is settling through a homogeneous uniform solution and it is non-accelerating, then the equation says that 6 pi r mu v equal to 4 by 3 pi r cube del rho g. This is what is? This is the gravitational force on the grain and this is the resistive force. These two will be balancing one another. 6 pi r mu. Mu is the viscosity, r is the radius of the grain, v is the velocity of the grain, Del rho is the density difference between the grain and the fluid. Del rho is the density difference between the grain and the fluid. G acceleration due to gravity. I repeat, del rho is the density difference between grain and the fluid. G is acceleration due to gravity. Mu is viscosity, and V is the velocity. Velocity of settlement. Velocity of settlement. So what will be V? V will be 2 by 9 mu r square del rho G. So the V will be 2 by 9 mu r square del rho G. Now, for a particular fluid and particular grain, what will happen? That del rho will be constant, G is constant, mu, viscosity is constant. So what will happen? That V proportional to R square. V proportional to R square. This becomes the, so the plus C log V 2 log R plus C. Now this relation will be valid till the grain size is low and the flow of the fluid surrounding the grain is laminar. But I repeat, this equation will be valid till the grain size is low and the fluid around it behave in a laminar way. But if we increase the size of the grain and if the grain size becomes 0.1 to 0.5 mm, then the flow around it becomes turbulent. Rather than laminar, the flow becomes turbulent. And the equation changes to log V equal to half log R. Instead of 2 log R, it becomes R plus C. It happens when you are increasing the size and the grain becomes more accelerating and there will be more turbulence around the grain. So the equation changes to 2 log R, it changes to half log R plus C. Okay?
Yes, sir.
Okay. Now, what actually we are trying to know? We are trying to know the size of the grain. So actually we are trying to know the R, the size of the grain. And that I am trying to reach from the settling velocity of the grain. So the settling velocity of the grain give me an idea that what is the size of the grain. Now again, the problem is that it is not possible to measure the individual grain settling velocity. How you measure there is a grain mixture, and can you measure the individual grain the settling velocity? It is not possible. So how we can come out with this problem of measuring the settling of individual grain? So we take the different process. One is a hydrosphere. Number 2, sedimentation balance. Number 3, centrifuge. Number 4 is X-ray and diffraction, light diffraction. All these are the. Now what we do here? what we do, that this is a density measuring instrument, that it basically sinks within a fluid and measures the density of the fluid at a particular level. Okay, it floats within the fluid and measures the density. Now you take a sample and you put this in the fluid. Now what will happen? It will immerse at a particular level depending upon the density of the fluid. And when you allow it to time for a time t0, and then this is t1. At time t0, it is basically measuring that the density at this particular level is this. You allow it to stand for a time, and then what will happen? The process grains, what were available at this site, at this level, it will get settled by that time, and the density at this level will decrease, and this will further sink. The density at this level has decreased, and it has further sank into the fluid. So what, and like that, you take the data at time t2, at time t3, at time t4. These are the data. So what this data is actually measuring? It is measuring the decreasing density of the fluid with time, because the coarser and coarser grains, they are getting settled, and the fluid is decreasing in density. The weighing machine or the weighing tube, that is basically going down and down. So the density measuring tube is going down and down. So if I make a curve that you have the time and this is density, so I can have a density of this that equal to 4.5 gram per cc, 4, 3, 2.5, 2. These are all gram per cc. So what you will be basically getting, that you will be getting that the curve will go like this. So your curve, so this is T0, T1, T2, T3, T4. So you have the different times, and the density is decreasing with time. So this curve will tell you that how the density is decreasing, and it will be a representative of the grain size curve, because depending on the size, the different sizes are getting settled and decreasing the density of the fluid, and that's why you are getting this curve, which is a replacement of the grain size curve. Now coming on to the sedimentation.
Sir?
Yes.
Sir, video is not clear. We are not able to see what you are writing.
Video not clear?
Yes, sir.
मैंने सुनाई नहीं दे रहा है।
सर सुनाई तो दे रहा है सर, दिखाई नहीं दे रहा है ब्लैक बोर्ड पे क्लियर क्या लिख रहा है?
No, is it because I am writing in the green pen, or it is because of the net issue?
Sir, maybe it is due to network. Yes, sir, it is blurred.
So let me write in the black pen. Now you can see. If I say hydrodynamic balance, can you see it?
सर क्लियरली नहीं दिख रहा है सर।
क्लियर नहीं हो रहा है
सर, शायद नेटवर्क इशू है सर।
तो क्या करेंगे? Should I proceed? दिखाई दे रहा है? Sedimentation balance.
Yes, sir.
Okay. I like in a larger size. Sedimentation balance. Now, what is happening in sedimentation balance? This is a sedimentation balance. You have prepared a solution of the sample. You have put a kind of pan within this, and connected it with a weigh meter. Now, what will happen? That if I made it at the time t0, then with time t1, t2, what you will be getting? That the sediment in suspension, they will start settling on this pan. And the pan will gain weight. As the time will go, that the sediment in suspension that is settling on the pan is gaining weight, it will go down. And as it will go down, gaining weight, that will be reflected in the weigh meter, that it is gaining weight. So, what kind of curve I will be getting? This is time, this is T0, T1, T2, T3, and this is the weight. So, you will be getting a curve like this. That with time, you will gaining weight. And that is actually a replica of the grain size distribution. That is a replica of the grain size distribution. These two, that is the hydrodynamic balance and the sedimentation balance, these two are used to identify for what grain size I am doing it. I am doing it for grain size which are smaller than 0.03 to 0.04 mm, and I cannot separate out those grains because of their cohesion. It can also be done by centrifuge. What is a centrifuge? In centrifuge, it depends upon the length of the arm and the velocity. Length of the arm and velocity, depending on these two, we can know that what length of the arm and what velocity is required to centrifuge a particular size of the grain. And the more you get, the more cohesive that nature, you require the more velocity to centrifuge and also to increase the length of the arm. It is also done by means of the X-ray analysis of the solution, X-ray analysis or light diffraction of the solution of different size of grains, the light diffraction and X-ray of different, and that, by that also people do that. Okay? Now come on to the sedimentary rock. So by this, actually what I tried to say, that how I measure from the pebble cobalt to sand size to the silt and mud size grain. That I basically discussed. That how the silt and mud size grain, that analysis is being done. Now, what happens when we do grain size analysis for the sedimentary rock? Suppose a Mesozoic rock, a Paleozoic rock, a Precambrian rock, the sedimentary rock. How we do the grain analysis? What I have discussed till now, it is for the unconsolidated sediment. I dissolve it in water. It is not possible that I dissolve water, rock into water. What will happen when I measure the grain size of the rock? Now, if the rock is carbonate cemented or it is loosely cemented, then you can do it by means of the carbonate cemented. So you can dissolve it in acid and the grain sizes can be measured. But that is very rare. Normally what we do, the grain size analysis of the sedimentary rock, we make thin sections of the rocks and see that under microscope and do the grain size analysis. Isn't it?
Yes, sir.
So we get the correct grain size by doing it under thin section? Because a grain can be elongated. And my section, I am cutting it like this. A grain can be flat, and my section is parallel to the flat grain, or my section is perpendicular to it. So all the grains are not in the similar orientation in a rock. Different grain are in different orientation, but I am taking the thin section on a plate. I am cutting the grain at a different angle. And how can I know the size I am measuring that is the correct size of the grain? It is not the correct size of the grain. So if I1 is the observed diameter of a grain under thin section and dr is the real diameter of a grain. So the relationship, there is an empirical relationship that people have derived from measuring hundreds or thousands of thin section, the size of the grain from thin section, and measuring their grain proper by separating the grain, and saw what can be the relationship of the measurement of a grain under microscope and its real size. There is a relationship that is basically established. The relationship is dr, the real, it is 4 by pi b observed. This is the relationship. That the real diameter will be 4 by pi, the observed diameter when you do it. But the thing is that we really do not do this exercise when we measure it from thin section. We do not really, after measuring, we do not transform by using this equation. Directly we use this data to plot the grain size data. Why? Because whatever the problem, whatever the shortcoming I am basically doing for measuring individual grain, that shortcoming is being propagated to all the grain. It is not that specifically for one grain I am doing it. So all the grains are equally affected. So relatively there is no effect between the relative sizes of the grains. Am I clear to you?
Yes, sir. Yes, sir.
So we understand that there is a problem. We do not use this in real life because there is relatively not much effect, because all the grains are suffered by the same sort. Okay, fine. Now we have measured the grain. Now the question comes, how to express the measurement of size? How to express what we have measured? What we have measured, how we will express it? Just 1 minute. So how we express? There are different ways of expression. Number one is histogram. Number two, cumulative curve. Arithmetic. Coordinate. See, cumulative curve. Probability. Number four, frequency. These four different ways that we basically represent our data. There are four different ways we basically represent our data. We will be discussing that how really we express our data. First, starting with the histogram, that what you are basically getting, we use here the different grain size scale. Grain size scale. Always in grain size measurement and its representation, it is a custom, worldwide custom, and everybody needs to follow that coarser grains will always be plotted towards left and final grains to the right. Coarse in the left, fine in the right. This is always needs to be followed for everybody in the world. And the percentage. So you get the bars. You get the bars. This is histogram. The different size grains, how really they are represented. This is very pictorial. Very pictorial. And even for a basic sedimentologist or basic geologist can easily understand what is the largest node, what is the biggest bar, and what is the maximum represented size in the population. It is not very difficult. But the problem is that the shape of the histogram will depend upon that what sieve sizes you basically used. I use 4, I use 4. So I get the histogram of 4. Somebody else use the same sample with 6. So he will get a histogram of the 6 bars. Which one? Which one I should take? I should take the 4 bar histogram or 6 bar histogram. Because the shape of the histogram will fully depend upon that the number of sieves I am used in the sieving, and so there is a subjectivity of the person who is doing the histogram and who is measuring the lenses. It is pictorial. It is very easy to understand, but there is a lot of subjectivity. And also, you cannot determine any statistical parameters such as mean, median, mode, sorting, skewness, nothing you can determine from a histogram. But this is pictorial, and if you can, suppose you are doing a mapping, and in the mapping you want to represent some portion of the map you have. So I am doing a mapping. In this area, I am mapping, and I can see that this side is basically unloaded. This is basically sandy part. This portion can be CT and then carbon. I want to represent the grain size, that the coarse grain size becoming fine this side. So I put the histogram of the different size domain, and then it can be easily anybody see, oh, here is the coarser grain dominated, is the middle size dominated, is the finer size dominated. So it is very pictorial kind of idea, but no one can say that exactly what is the mean, median, what size actually, that you can, it's very difficult to say. So then the question of cumulative count, that cumulative. So cumulative count with arithmetic coordinate and probability coordinate. If the cumulative curve you do with the arithmetic coordinate, then you will be using the pi size of the pi size. If you do it with the probability coordinate, then you will use the millimeter size. Then the grain millimeter size I will be choosing. If the arithmetic coordinate, then I will be. Okay? And you know the course. So this is the cumulative percentage frequency. Okay? And 1, 2, 3. You can say -1, 0. This is a pi. And this is 10, 20, 30, 40. That is the arithmetic. And I am doing it with the arithmetic coordinate. Arithmetic coordinate, I have used the pi scale. Yeah. The codes are on this side, the pi are on this side. Now what I will get that in this kind of scale, that is the arithmetic scale, I will get a curve which may be S7 curve. S7. Okay? S7 curve. Actually what I am doing, I am starting with a normal distribution problem. Normal distribution of. What is a normal distribution of the grain? That there should be a central tendency. There should be a central tendency, and lesser grain will be on the higher and the lower side of it. This is the normal distribution. And if I get a normal distribution, what kind of curve I expect? I expect a symmetrical Gaussian curve. Symmetrical Gaussian curve. So this is a normal distribution. There is a strong central tendency, and lesser to the coarser and lesser to the finer size. That is what we call it a normal. If it is very much biased towards the coarser side, will it be normal? No. If it is very much biased towards the finer side, will it be normal? No. There should be a central tendency and lesser both towards the coarse and the fine. Then you call it a normal distribution. And a normal distribution, if you plot here in the arithmetic scale, then you get this kind of a pattern. Now if I replace this, now what is the meaning of this? Suppose here I get that this is suppose 32 here, and that is basically represented by 0.55. What does it mean? 32% of the grains are coarser than the size represented by pi 0.5. That means 32% of the grains, they are coarser than 0.5. So that's why this much is coarser than 0.5, and this much is represented by 30%. So when we say that pi 0.5 equal to 32, that means that 32% of the overall population is coarser than the size that is represented by pi 0.5. Is it clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now I replace it by the probability word. Now, what is probability coordinate? That which is very squeezed in the middle. cumulative percentage frequency. Now what we will do? We will use the millimeter scale. Millimeter scale. So in the millimeter scale, I can have the 2.5 to 1.8, 1.6, 1.2. These are all millimeters. Okay. Now, what is this probability coordinate? That it is very extended at the 2 limit. From 99, it is struggling to reach 100. It cannot reach 100. It can maximum reach 99.999. It is struggling to reach 100. It is also struggling at the beginning. It is not reaching to the 1. 0.1 to 1 reach 100 both struggle kar raha hai. But it is very squeezed in the middle. Very squeezed. 10, 20, 30, 40, 50. So it is squeezed in the middle. That is the probability. Probability ordinate. We will do this plot with probability ordinate. And if we plot this normal distribution, which in the arithmetic coordinate, it takes a S shape. In the probability ordinate, it will be basically plotted as a straight line. As a straight line. In the why? Because it was earlier in the arithmetic it was like this. Now I am keeping it and stretching it. Both this end and that end. I am stretching by this scale and making it straight. Am I clear?
Yes, sir.
Yes, sir.
So
Yes, sir.
arithmetic frequency scale is the sigmoidal pattern. It becomes a straight line when I make it on a probability frequency curve, and it is basically stretching it and making it a. Now the question is, yes, I do believe that it will be a straight line. Now, where will be the straight line? Here. What will be the gradient of the straight line? Which will be here, like this, or like this. What? How will be the straight line? How will be the straight line? Where will be the straight line? What will be the gradient of the straight line? What guides this? The position of the straight line, that whether it will be here, it will be here, it will be here, it will be here, it depends upon the average grain size of the distribution. It depends on the average grain size. If your average grain size is 4 star, then your line will be on this side. Average grain size is finer, your line will be shifted more toward this side. Average grain size. And what will be the gradient of the line? Gradient of the line, that will depend upon the sorting of the distribution. Sorting of the distribution. Sorting of the distribution. The more well sorted, that the line will be more steeper in the gradient. More well sorted, more steeper. Because if you have a steeper, you are actually representing the grain size this much grain size interval you are representing. But if you are a gentler, you are representing this much grain size. This much grain size you are representing. This is the more poorly sorted grain size you are representing. Whether you have a steeper slope, you are basically representing much narrower grain size, much smaller grain size. Suppose I basically plot the age of all the students in your class. What kind of straight line I will get? I am expected to get a very steep gradient line. Very steep gradient line where you all are clubbed in a very narrow age group. But if I club all the students of the department right from the BSc 1 to the MSc final year and plot it, then the gradient of the line will become more gentle because you are basically putting it on a large number array of the age, about 5-6 years age, that is the age group, and the gradient of the line that will become more and more gentle. This is what is called the sorting. Is it clear?
Yes, sir.
Okay. Now we will come on to the frequency. What is the frequency? A frequency curve actually measures the slope of a cumulative curve. A frequency curve actually it is almost similar to a histogram, and it actually measures the slope of a cumulative curve. Now, how we do it? You have cumulative frequency. This is grain size. Now, if I make a tangent on this, okay, and if it is 2 and it is 3, then how much this tangent will rise between these two? So within 1 pi, this is 1 pi. 1 pi, that is the slope. You are basically taking the slope of this line. You are basically, and then you plot it. We get half pi interval and 20, 40. This is the percentage. So you go on plotting the half pi interval, and the percentage it represents with respect to the half pi interval, you get a frequency curve like this. So basically, this is the cumulative frequency. This is the cumulative percentage frequency curve. You are measuring the slope of that curve, and each half pi interval, what is the slope that you are basically plotting. Each half pi interval, what is the slope that you are plotting. And that slope, the slope is the maximum, steepest slope that you are getting as a height here. That is the highest, most probably, most commonly abundant size. It is representing the most commonly abundant size. And we call it a frequency. Frequency curve is actually very good when we will be dealing with a bimodal sandstone. There are more than one mode of grain size, and it will very easily pick up the individual mode. Because that, then the cumulative curve, if you go on measuring each half pi interval, the slope of the cumulative curve and plot it, then the frequency curve, it shows you the bimodal curve. And that bimodal curve very easily can be identified as a bimodal distribution, and bimodal sand distribution that has a huge implication about the provenance. Okay, now we have represented the grain size. Now we have represented the grain size, and we have plotted it. Now, what we will be doing with this plotting? What we will be doing with this plotting? We will be trying to determine the different statistical parameters. Different statistical parameters. Different statistical parameters. That is mode, median, mean. Now, what is mode? The most commonly occurring grain size. most commonly occurring grain size. How we get it? The steepest point, the most highest gradient point of cumulative curve is actually, it is a very tentative way to get it. Very tentative way. What we do, suppose this is a cumulative curve, we'll choose that what is the maximum steep. Suppose this is this, I choose this is the most steep portion of the curve. Then what we do, that we see the frequency half pi, 1/4 pi on this side and 1/4 pi on this side. Or you can do it half pi. So if I choose this is my mode, then half pi to the final direction, half pi to the coarser direction, what is the frequency that I will see? Then I move by 0.1 pi or 0.2 pi. Again I measure half pi coarse, half pi fine. So it is a trial and error. I visually choose one point, identify it as a mode, then see the one fine interval frequency by measuring half pi finer and half pi coarser. Then I shift my point by 0.1 pi or 0.2 pi. Again measure the 1 pi interval frequency and then plot it which one is the maximum that I identify as. So it's a trial and error method, and this is how we identify the mode. The problem is that this only talks about the central portion, that what is the maximum. It doesn't talk about anything about the end of the curve. Problem in it is that it doesn't talk about anything about the extreme of the curve. It only talks about the most abundantly present grain size in the distribution. Okay? Then the median. What the median says, that the size 50% of the distribution is more than this size and 50% less than this size. That is the median. The 50% grain size distribution, that will be more than this size and 50% less than this size. Then the median. The most, now this again talk about the 50%, not talk about that what is happening at 84%, 90%, not talk about what is happening in 10%, 16%. Not, they're not bothered at all. Just I am bothered about their median size. Not at all bothered that what is happening that in the extreme of the, suppose a sandstone with 10% clay and the sandstone with 10% pebble, both will be same in this. There will be no difference between a sandstone with 10% pebble and sandstone with 10% clay if I do the mode and the median. Both will show the same mode and same median. Am I clear? Because it is not talking about the extreme. 10% clay or 10% pebble, it will all come in the extreme. Not come in the middle, that is the maximum, that is the sand. All, in both the cases, the most dominant is the sand. The thing is little improved when we talk about the mean, where it is said that 516 plus 550 plus 584 by 3. So people have tried that a little increase the portion of the curve in the calculation. Taken the 516, 584, and then it is little better than the above two, because it is taking at least 68% of the curve. 16 to 84, 68% of the curve. Okay? Now, this is mean, median, mode, median and mean. Then come on to sorting. The first sorting, first person who talked about sorting, this is the Trask sorting coefficient. Root over of mm25 by mm75. This was the formula given by Trask and told that how it is given in the millimeter scale, and the relative distribution of the 25 mm and 75 mm, that means 25% of the mm size of the grain which is at 25% and mm size of the grain which is at 75%. That's what it means. Mm size of the grain which is at 25% of the distribution and mm size of the grain at 75% of the distribution. And then they say that if this is 0.3 to 0.5, then it is a very old sort. Now again, the problem remains that how really you take it. This is also then changed to what we call the pi quartile deviation. Okay, so pi quartile deviation that basically say that rather than these, they say that instead of mm, they took it to the pi scale, that pi 75 minus pi 25 by 2. So it is in the millimeter scale and it is a ratio. They removed the ratio and the millimeter scale and they said that no, it will be pi 75 minus pi 25 by 2. And then they say that if you have 1.3 to 1.5, that will be very good as a sorting. But again, the major problem that remains, that people say that you are only considering the 50% of the card, not actually talking about the extreme of the card. How we can extend into the extreme of the card. So the question of standard deviation, that came. Standard deviation. And graphic sorting that came based on the standard deviation. That means 2 sigma. That from 16 to 84, if 50 is the middle, then the 16 to 84 it represents 2 sigma. 2 standard deviation. So the graphic sorting, they say that no, we will not consider 75 and 25, we will consider pi 84 minus pi 16 by 2. Because 84 and 16, they are basically representing the 2 sigma. And if there is a central tendency, and from central tendency, if I have 16 and 84, they will be basically representing sigma and sigma, the total 2 sigma will be represented. This has been further improved by what we call the, and which is now basically considered as inclusive graphic sorting. Inclusive graphic sorting. To increase the further consideration of the part of the card. That's how we call the inclusive graphic sorting. The formula, this is called sigma G, this is sigma I. 584 minus 516 by 4 plus 595 minus 566. This is the inclusive graphic sorting. So what is this? This is actually covering the 68% of the car. This is covering 90%. And then you are basically making average of them. So this is the 2 sigma. This is 3.3 sigma. And then when you make the average, then the formula comes 584 minus 564 594 minus 566. This is the inclusive graphics. And there are, when you measure these sizes and plot it in this equation, then there are certain subdivisions that you get the very well sorted, moderately sorted, poorly sorted, very poor sorted. So those are some of the values that you can get in any book. That what are the values that say that. So if you have the values less than 1, then you have a well sorted. If the values is more than 1, then you are more and more poorly sorted. This is the general thing I am telling you. But further subdivision you will get in any book, because the sorting value. So basically, if you have the 1, that means that less than 1, that means it is you are more well sorted. Okay. Is there any question?
Sir.
Yes.
Sir, I did not understand the standard deviation.
Standard deviation is if there is any distribution, that distribution may be well sorted distribution, as I discussed in your class, the age group in your class, or it may be a poorly sorted distribution. That means if I consider all the students of the department and then plot it, there is a wide range of data that the data is varying. So how the data is varying with respect to the central tendency. So if I have a curve like this, then there is a central tendency. And from central tendency, this and this, and what way they are varying on the either side of it. That is what is called the standard deviation. Okay. So this deviation from the standard, the central tendency, that is what we call the sigma and sigma. Then if it is a 16%, this is 84%. Then when you plot it in the cumulative curve, this will become 16, this will become 84. So and this becomes the 50. So this entire range, this is a standard deviation with respect to the central tendency 50. Then you call it a sigma. This is a sigma. So if I consider the entire distribution, how it is varying from the central tendency, that is what is called the standard deviation. And since we want to represent from our statistical analysis that how really the entire grain size distribution they are behaving, we cannot remain confined in the central tendency, which is actually a mean or mean, the mode or mean is doing. We have to talk about the entire distribution. What is happening if you see, as I have given an example, a sand with 15% pebble, and a sand with 15% mud. Are their hydrodynamics, are their depositional environment same? Definitely not. Total energy condition is different. I cannot be oblivious about the extreme of the curve, because either 15% pebble or 10% mud, they will come in the extreme of the curve. I have to take the extreme of the curve. this standard deviation actually allow me to take more and more extreme part of the curve. Is it clear?
So, sir, how do we know that which type of sorting calculation we have to follow in a particular calculation, or means if we have to calculate the sorting in a certain grain? So how do we know?
Size distribution.
Yeah, sir.
It is not a single grain. There are a large number. You are doing it in a setting.
So, sir, which calculation of sorting should be used? How do we know that?
No. What I have said, that the inclusive graphic sorting, that is the equation everybody uses. I only discussed with you the evolution of it. How from the initial that they considered the 25 and 75, from there they evolved to 84 and 16, and then finally they took into its account 95 and 5 and give a shape of the final equation. Nobody uses the earlier equations now. Everybody uses the last equation that I have said, is 584 minus 516 by 4 plus 595 minus 55 by 6.6. This is the equation everybody uses because the equation has been evolved. And now this is the equation that has been used for all the grain size distribution calculation, the sorting distribution. No other equation is used.
Okay, sir.
Now we come on to the skewness. What is skewness? Skewness is the asymmetry of the curve. Asymmetry of the curve. Okay? That is skewness. Now, what do we mean by the asymmetry of the curve? That means it is not a symmetrical curve and it has a tail. It has a tail either to the coarse side or to the fine side. That means if I have a normal curve like this, but I can have a curve like this, I can have a curve like this. So this is a normal curve which has a central tendency and similar distribution both coarser and the finer side. But this is a curve which has a restriction in the coarser side, but there is no limitation in the finer side. We call it positively skewed curve. Positively skewed. And this is a curve which has a restriction in the finer size, but no restriction in the coarser side. We call it negatively skewed. And both these curves, they are skewed curves. They are skewed. They are asymmetric. They are not symmetric. And how we define the asymmetry? How we define the asymmetry of the curve? How I define the asymmetry of the curve? Now this is a asymmetric curve. How I quantitatively determine the asymmetry of the curve? how I quantitatively define the asymmetry of the curve. Now, this is phi 16 and this is phi 80. If it is a normal curve, then phi 84 plus phi 16 by 2, this should be equal to phi 50. Isn't it? In a normal curve, because it is the 2 sigma standard deviation, and if Q standard deviation, I take average, it should give the central tendency, as I have already defined. Now, what I see, that if I see the 16 and 84 and I make an average, then the plot comes here. Whether my curve is passing through this point, from here, my curve is passing through. So that means curve is supposed to pass through this point, but curve is going through this point. That means this A, the difference between the two, this is the asymmetry. This is the asymmetry, which we should not get, but we are getting. Because the curve is asymmetric, it is not asymmetric. So, what is the asymmetry? What will be the asymmetry? But how I express the asymmetry of this curve? I express the asymmetry of the curve A by sigma. That sigma is this. So, what is A? A will be phi 84 plus phi 16 by 2 minus phi 50. This will be A. This will be A. Phi 84 plus phi 16 by 2 minus phi 50. This will be A. And what will be sigma? Sigma will be phi 84 minus phi 16 by 2. This is sigma. So if I do A by sigma, this becomes phi 84 plus phi 16 minus 2 phi 50 by phi 84 minus phi 16. Okay. Am I clear? Is it clear to you?
Yes, sir.
Okay.
Yes,
This is what is called the asymmetry of a curve. And then taking this into consideration, the inclusive graphic skewness equation that has been framed, inclusive graphic skewness has been framed. And what is that equation? Phi 16 plus, जो मैं अभी draw कर रहा हूँ, minus 2 phi 50 by phi 84 minus phi 16 plus phi 95 plus phi 5 minus 2 Just 1 minute. सब बताइए. नमस्कार. So when he will be able to do that? So by 15th you will be released. By 15th. Okay. Okay. So मैं रोड से बात कर लूँ एक बार. अच्छा तो उनको फिर चाहिए वो जो उनसे मैंने करते हैं आपको फिर ले लेकर उनको चाहिए होगा वो देने होगा. That let me talk with you. ठीक मैं आपको कॉल करूँगा. Okay. So now this is the final inclusive graphics skills. What they did, they only increased the part of the card by adding the 95 icon. So you can my discussion you can be very clear. The entire process is to include more and more part of the card, and that is the intention that you are. Am I encroaching others class? Is there any class after this?
Yes, sir. We do have a class at 11:40.
11:40. Okay, I have just only topic left so that I will. So this is the skewness, and then the final what I will be discussing, that is the pickedness of the car. Pickedness, what we call the kurtosis. Somebody say kurtosis, or whatever you say, that is the kurtosis. What we call the pickedness of the class. Pickedness. But they say that high 95 minus 5 by 1.44 high 75 minus 525. Sorry, 2.4. This is the equation. That means how the central part of the card, that is 75-25, how it is represented with respect to the extreme of the card. That if you have this value is equal to 1, that means this distribution and this distribution, they are similar to one another, and I get a normal Gaussian type. But if this central portion is better represented than the extreme portion, that means the card will be like this. The central portion better represented than this. But if the extreme portion of the curve is better represented than the central portion, then the curve will be like this. You call it leptokartic curve, leptokartic. And this as a platykartic. Normally, in a normal distribution, the distribution between 95 to 5, it should be 2.44 times to 75-25. If it maintains this, then the curve is normal. There is no problem. If this portion is more represented than the extreme portion, then you get this shape, you call it leptokartic. And if the extreme portion is better represented than the central portion, you get the curve this time. One extreme of this platykartic curve is the bimodal curve. That means you get this and then there is a low, there is another. So there is a bimodality. That bimodality is one extreme of the platykartic curve. And what is the meaning of that? That we will be discussing in the next class. I request the seer. Who is seer?
Yes, sir.
Seer should take the attendance and send it to me.
Okay, sir. Okay, sir, I will do it.
Okay. So I leave it here. You have another class. I will not continue. Okay.